Good afternoon. Welcome to NASA headquarters in Washington, D.C. My name is Dwayne Brown from the Office of Communications. Today, we're going to take a trip to the solar system and beyond. Recent news headlines around the world have reported NASA findings of large amounts of water long ago on Mars, but present today on other bodies in our solar system. We know this because at NASA, in the solar system and beyond, we're out there. The news of water is not only intriguing to scientists, but could humankind perhaps be getting even closer to answering, where do we come from? Where are we going? Are we alone? Today, you hear what the experts have to say. We'll have brief remarks and presentations, and then we'll open it up to questions here in our audience, our phone lines, and social media. And there is a lot of buzz on social media on this subject. Send in your questions to #AskNASA. Before we get started, let me introduce you to our unique folks here on the stage. First up, Dr. John Grunsfeld, 5-time Space Shuttle astronaut and associate administrator for the Science Mission Director here at NASA headquarters. And let me add that out of those 5 flights, 3 times, Dr. Grunsfeld serviced the Hubble Space Telescope, and this month, humankind celebrates 25 years of the Hubble and operations in space. I think that deserves a round of applause to the Hubble team, ladies and gentlemen. Following Dr. Grunsfeld is Dr. Jim Green, Director of Planetary Science here at NASA headquarters. Dr. Jeffrey Newmark, Interim Director of Heliophysics at NASA headquarters. And Dr. Paul Hertz, Director of Astrophysics at NASA headquarters. And Dr. Ellen Stofan, NASA's Chief Scientist. Fasten your seatbelts. Let's go to the solar system and beyond. Over to you, Dr. Grunsfeld.
Thank you very much. As you know, our job here at NASA is to innovate, explore, discover, and inspire. And I believe the science program really epitomizes that mantra. We try and answer fundamental questions, as you heard Dwayne say. Where did we come from? Where did the bits that we're made out of come from? Where are we going? What's the fate of the universe? And are we alone? The question of, are there other beings out there of any kind? Science right now at NASA is exploring the sun in great detail, from Mercury with the MESSENGER spacecraft still orbiting Mercury, out all the way to Pluto. New Horizons spacecraft will reach Pluto this summer and beyond with Voyager. And of course, we have MAVEN that just recently arrived at Mars, studying the atmosphere and current loss of the atmosphere at Mars. Dawn has just arrived at Ceres. Cassini is still studying Saturn and the moons of Saturn. It's really an amazing exploration of our solar system and much more. Beyond, we have Hubble celebrating the 25th anniversary of time on orbit. And it's kind of neat to think about all of our students today in grade school and high school and college who have lived in a world and have always known Hubble. Kepler has told us that we live in a galaxy and, in fact, a universe that's filled with solar systems. And many planets that may resemble Earth in being a rocky planet in a potentially habitable zone. Hubble and Spitzer have allowed us already to follow up by studying the atmospheres of some of those planets. And the James Webb Space Telescope, which will launch in October of 2018, will allow us to explore in much more detail the atmospheres of planets around nearby stars. Here on Earth, we live on a water planet. And water is essentially everywhere. In some cases, literally everywhere. And water is critical for our life on Earth. And we've seen that now from our Earth observing constellation that, the propagation of Earth, our water cycle, is a very critical thing to understand that we can only understand from space. We just launched the Soil Moisture Active Passive mission to look at that tiny amount of moisture in the soil. And we know from the current drought situation in California and our American West how critical that is. But water is everywhere in our solar system as well. And we're seeing that through our various missions, and you'll hear about that. In our quest to answer the question of are we alone in the universe, we're looking for other habitable environments, besides here on Earth, of course. And we're seeing that environment in many different places. You'll hear a little bit about our Mars rovers that have established that Mars was once habitable. And Mars has water today. It had freshwater lakes and its own water cycle, but it also has organics. We've seen a methane signal. We know that there are nitrates in the Martian surface. It's currently a habitable environment, but we don't know whether there was or is life on Mars. And we're seeing in some of the icy moons the tantalizing possibility that there are oceans that have been around for billions of years that would also provide a habitat for primitive life. And we're very happy this year to be able to say that we're starting a mission to go study the moon of Jupiter, Europa, to see if it perhaps has signs of habitable environments or perhaps even life. This is just a grand time to be exploring science, to be exploring our solar system and beyond, and I look forward to all your questions. Jim Green.
Thank you very much, John. What I'd like to do today is to talk a little bit about some of the fabulous observations that John mentioned and a number of others. And we'll start, of course, with Mars. Mars, like Earth, is in what we call the habitable zone, the region that extends around the sun, for which the sun's light on a body about like the Earth is such that water can exist in three phases: liquid phase, solid, and vapor. Now, today, Mars, although it's in the habitable zone, is a very arid planet. And if I can have my first video, what we've discovered using our assets at Mars, looking at the terrain and our ground truth observations from all our rovers, is that Mars in its past had a significant amount of water. In fact, as John mentioned, it had a habitable environment. Curiosity is in a region where water flowed pretty rapidly. So when we think of Mars in its past, we recognize that it was a water world, much like the Earth. It had clouds, it had oceans, and a hydrological cycle. But the most recent observations that are really tantalizing are those that were made with ground-based telescopes in the infrared. These telescopes were looking at the north polar cap of Mars for what's called the deuterium to hydrogen ratio. This is called the D to H ratio. And once we make those measurements and we compare them with Earth, we then can extrapolate back in time how much water really existed on the surface of Mars. Now, I mean water. I don't mean ice, and I don't mean the vapor. And what we find out is really illustrated in the next video. Here we see Mars as it was in the past, but now we're going to paint the oceans. We're going to strip away the clouds. We're going to look through the atmosphere. And what we find is that about 50% of the northern hemisphere of Mars had water. And it had it for a very long period of time, perhaps more than 1 billion years. Current thinking is about 1.2 billion years. Now, in fact, some of this ocean was as much as 1 mile deep. Now, Curiosity is sitting in a crater, not on the ancient shore line of where this ocean would be, but a little inland. But what we do know and what we have found out is that water cycle on Mars was such that it popped over the crater wall, flowed down into the crater, and in fact did this repeatedly over perhaps millions and millions of years, and actually built up that large mountain called Mount Sharp in the center of Gale Crater. So Mars was much more Earth-like in a habitable zone for a very long period of time than we ever imagined. This is really an exciting time. Now, just beyond Mars is a region called the asteroid belt, but it's also a location for which the solar energy is such that beyond a certain location, we call the snow line, further out than the snow line, we find water should be only in one phase, only in the solid phase. But what we're finding is that's not true either. If we look at the next, my first graphic, here we see what Galileo saw 400 plus years ago, the Galilean satellites, the moons of Jupiter, Io, Europa, Ganymede, and Callisto. And as you can see, they're ordered in such a way with Io close to Jupiter. And the gravity interaction between Jupiter and the moon Io is such, with tidal forces, that it literally heats the inside of Io. It turns it inside out. Io is a very volcanic world. Don't expect any water there. However, the next one, Europa, we're finding at much different location. It's far enough out that the tidal forces don't dissipate its ice shell, but retain enough water in liquid form below an ice crust to really make it an exciting place to look at. So if I can have the next slide. Most recent observations from Hubble have really tantalized us in going to Europa as our future mission. Here we see potential plumes of material, ice, water, ice, flowing out from cracks perhaps in Europa in the southern hemisphere and recoating the surface. This must be what was happening because the surface of Europa is very little cratered. This is just a tremendous set of observations. But even more recently were those, in my next slide, of Hubble observations of aurora on Ganymede. Now, Ganymede is a huge body. It is the largest moon in the solar system, larger than our own moon. It has a magnetic field, which is also a very bizarre thing for a moon to have. But that magnetic field, as it interacts with Jupiter's magnetic field, allows particles to be exchanged between the two planets, or the planet and the moon, Ganymede. And this produces aurora. Now that's great. We can observe this aurora. We've seen the aurora many times, but when we do a detailed analysis of the aurora, we find out something very important. Now the magnetic field of Jupiter actually is pretty twisted. And by the time it gets out to Ganymede, it can really rock back and forth as Ganymede moves through the magnetosphere of Jupiter. We therefore expected the aurora to rock back and forth, but it doesn't. It rocks very little. Now this means that some sort of current arises underneath that ice crust, generating another magnetic field that then stabilizes this aurora such that we see it in a particular place. From those data, we now know that indeed Ganymede has an undercrust ocean. Now we only are just getting tantalizing glimpses of that, how deep it is, but it must be a vast body of water. This changes our perspective of where habitable zones are completely. My next slide. Here we see those Galilean satellites once again. Io is closest to Jupiter, but it's a volcanic world. It's not an icy world. But we know now that Europa and Ganymede have a significant amount of water underneath their ice crust. And in fact, we now believe Europa has perhaps twice the amount of water underneath that ice crust that the Earth has on its surface. With the latest Hubble observations, we're going to include Ganymede now in that habitable zone because water is incredibly important. Now, there's some ideas that there may be water in Callisto, but we haven't confirmed that. But at least now we recognize that habitable zones aren't just around stars, but they can indeed be around our giant planets. What we're finding out is that the solar system is really a soggy place. Now, all these bodies, of course, are sitting in the solar wind, and that changes the dynamics of the water and the atmosphere as they interact with the solar wind. And for that, I'm going to turn to Jeff to explain.
Thank you, Jim. Indeed, all the planets and moons that Jim just talked about are actually embedded in the solar atmosphere, the extended atmosphere of our sun. What we're trying to do is understand how the sun interacts with the planets, the moons, and this as a connected system. If you could please run my first video. What we see here is a model of the inner solar system. You see the planets. And what we want to do is understand how the sun, what it's varying, what is driving the solar wind that Jim mentioned, and how it interacts with planets here, and in fact, planets elsewhere, how other stars, how their winds interact with planets throughout the universe. Well, as we'll see, this interaction actually also involves the distribution of water throughout our solar system and indeed throughout other planetary systems. In this model here, what we see is a series of solar storms. We call them coronal mass ejections, or CMEs. This is a model of a series of events from 2012. And you see these large-scale events leave nothing in our solar system untouched. These are tremendous events with a tremendous amount of energy. This is billions of tons of material traveling millions of miles an hour throughout interplanetary space. And indeed, understanding how these interact with our planets is crucial for our understanding of the life cycle of water on these planets and indeed for habitability throughout the universe. The constant streaming of the solar wind and the solar storms impacts the ways that our planets and other bodies of the solar system in a wide variety of ways. As Jim described, Mars was covered by water 3 to 4 billion years ago. However, as we know today, it is drier. What may have caused this change? And what role did the solar wind and the sun have to play in this? It is thought that some 3.5 billion years ago, extreme interplanetary conditions caused by our sun may have caused the much larger rate of water loss in the Martian atmosphere. You can run my next video. We see the changes in Mars. However, how did these changes come from the solar wind? Well, and why didn't they affect the Earth? What are the differences? The Earth, in fact, is protected by a magnetic cocoon we call the magnetosphere. However, Mars does not have a significant magnetic field. So this absence of the protection allows the supersonic solar wind to interact directly with the Martian upper atmosphere. And it strips away the atmosphere and the water from the planet, as you see here in this model, based on new observations from MAVEN, in fact. And so we see that the interaction of the solar wind directly affects the life cycle of water. Comets, the next part of distributing water from our solar system, these carry ingredients vital to life as we know it. As the sun heats comets, the water and dust and the chemicals scatter and are distributed the water throughout our solar system. Similarly, this occurs through distant stars and planets around other systems. In my next video, we see actual observations from our stereo spacecraft. This shows the solar wind interacting with there's actually two comets in this video, one comet Ison and the other comet Encke. And we see their tails being distributed, again, blowing water and dust throughout the solar system. In this video, actually, the sun is off to the right, and you get a very interesting perspective of relative positions of Mercury and Earth, in fact, because stereo spacecraft are on the far side of the sun from us, looking back at this. So we've talked about the solar wind. Where does this come from? We know it comes from the sun, but how is it accelerated? How is it driven? Where do the CMEs start? In my next video, you'll see in 2018, NASA will launch the Solar Probe Plus mission. This will, for the first time, fly into the sun's direct lower atmosphere, traveling closer than 4 million miles to within the solar surface. This historic mission will revolutionize our understanding of the sun's atmosphere and how it's heated and how the solar wind is accelerated. In the video, you see the Solar Probe Plus spacecraft and its orbit through the inner part of the solar wind where it's being accelerated close to the sun. Here we'll understand the magnetic fields, the particles, how they're accelerated, and again, what drives this process of distributing water throughout the solar system. Once we do this, this will help us understand our star, what powers these storms, and again, looking at as an analog for solar systems throughout our galaxy. In my last video, you'll see a large exoplanet. Here, this is weathering the impacts of a stellar storm. These storms occur through stars everywhere. In this animation, which is actually based on observations, we see the material from the planet's upper atmosphere being driven away from this stellar storm, exceeding 300,000 miles per hour. And now, Paul will provide details of these other stars and the habitability of planets elsewhere.
Thanks. So Jim and Jeff have told you about habitability and water in our own solar system and the impact on the habitability of planets from the sun. And so I'm going to talk to you about habitability in the rest of the galaxy. Looking beyond our solar system, we see lots of water. The galaxy is also a soggy place. We can see water in the interstellar clouds from which planetary systems and stellar systems form. We can see water in the disks of debris that are going to become planetary systems around other stars. And we can even see comets being dissipated in other solar systems as that star evaporates them. But the place that we're most interested in looking is at worlds in the habitable zones around stars other than our sun. So my first graphic is a little illustration of what the habitable zone means. Planets which are too close to the star are too hot for liquid water to exist on the surface, and planets which are beyond the snow line are too cold for liquid water to exist on the surface. But planets in the habitable zone have water that can exist liquid on the surface. We're looking for rocky planets that have surfaces that could hold water. This would be the habitable zone, and the only place we know of where life, like life on Earth, might exist. 20 years ago this year, the first planet around another star, or exoplanet, was discovered. A planet was discovered around the star 51 Pegasi in 1995. Thanks to NASA's Kepler Space Telescope, which was launched 6 years ago, we now know of over 5,000 worlds around other stars. We now know that just about every star in the galaxy has planets around them, probably multiple planets around them. The most common sized planets that we've seen around other stars are planets that are between the size of the Earth and Neptune in our own solar system. Now, the Earth is a rocky planet, and Neptune is a icy giant without a solid surface. And the dividing line between them is somewhere around twice the size of the Earth. So we're very interested in finding planets that are between 1 and 2 times the size of the Earth around other stars in the habitable zone. In my next graphic, I show you the very few that we've discovered so far using the Kepler Space Telescope. About a half a dozen or more rocky planets in the habitable zone of their stars. And planets like these are the prime locations where we would like to be able someday to look for evidence of habitability on these planets. The question is, how do we look for that? Oh, one more thing before I move on to that. In the year 2017, NASA will be launching the Transiting Exoplanet Survey Satellite, or TESS. And TESS is going to find rocky planets in the habitable zones around the nearest stars to the Earth, the nearest stars to the Sun. It'll be finding many dozens of these. And because these will be planets around the nearest stars, they will be the prime planets that we'll want to follow up and look for signs of habitability. But how do we look for those signs of habitability? Well, right now, what we do is we wait until the planet passes in front of the star and watch the star's light filter through the planet's atmosphere. This method is called transit spectroscopy. And when the starlight filters through the planet's atmosphere, the atmosphere absorbs some of the light, and the different molecules in the atmosphere absorb different colors of light from the star. And these fingerprints of absorbed light are the indicators of exactly what kind of molecule is in the planet's atmosphere. So we could detect water, carbon dioxide, methane, and other molecules through this methodology. So if you look at my next graphic, these are some of the kinds of planets that we're trying to use this transit spectroscopy on. We've been successful at using this method with 2 of NASA's space telescopes, as John mentioned. The Hubble Space Telescope and the Spitzer Space Telescope have both been able to use transit spectroscopy to look at the atmospheres of gas giant planets that are very close to their stars, in the hot zone of their stars, because these are the planets that have the most light filtering through them and also are around the brightest stars, so we get enough signal. It'll take the next generation of space telescopes for us to be able to extend this methodology to ocean planets smaller than the gas giants. And in 2018, we'll be launching the James Webb Space Telescope. And one of the scientific investigations that it'll be capable of doing for us will be doing transit spectroscopy, investigating the atmospheres of some of the ocean world super-Earths around the nearby stars, the planets that TESS discovers, and looking for the signatures of habitability gases in those atmospheres. But eventually, we need to develop new techniques for studying the atmospheres of rocky planets in the habitable zones of their stars. Now, these planets are going to be smaller than the ones we're studying so far, which makes them fainter. But they're also going to be further away from the star because they have to be in the cooler habitable zone than the hot zones we're looking at now. That means they're very, very faint. And we're going to have to use a new technique, direct imaging, in order to be able to measure their atmospheres. So my next graphic is a simulation of what such an image might look like through a future space telescope, one that NASA is currently studying called the Wide Field Infrared Survey Telescope, or WFIRST, equipped with a special kind of camera called a coronagraph. The coronagraph is capable of blocking out the light from the star and revealing the light from the planets surrounding that star. These planets are over 1 billion times fainter than the star, so this is a very tricky optical problem. But in this simulation, the star's light has been constrained to inside the red circle, and it's been blocked out. And you'll see that in the upper left, a planet has been revealed, which would be a large Jupiter-sized gas giant. And in the lower right, just outside the red circle, you can see an Earth-sized planet has been revealed in this simulation. And if this telescope works correctly and the right planets are around the nearby stars, we would be able to look at the light directly from these planets and investigate what kind of gases are in their atmospheres and are giving us the spectra we look at. So not only is NASA studying water and habitability in our solar system, but we're also starting to look for water and habitability on planets around other stars, and we're building the capabilities we'll need to be able to look for actual habitable rocky worlds around stars other than our own sun. Ellen?
You know, obviously what we've been talking about here today is water. Why is water so important? We're looking for water. I want to bring you back to the Earth for a minute. Now, think about the fact the Earth formed about 4.6 billion years ago. By about 3 billion years ago, life evolved here on Earth in the oceans. And for billions of years, it remained in the oceans. So that's certainly one of the things that really drives us to look for these watery worlds, either in our own solar system or beyond our solar system. But you know, it's even more than it's just the experience of what we understand here from the Earth. It's the fact that the water molecule has these really unique properties, we think. It's a solvent. It moves things around. It has really unique properties that we think are really critical to the formation of life, not just here on Earth, but on other bodies in the solar system. Now, when you look at the bodies that we've been talking about here, that Jim Green and Jeff and Paul Hertz were talking about, that you see in this graphic, you know, Mars there in the top center, so critical, we think, to this search for life because of the fact that water was stable, as Jim was saying, for possibly 1 billion years on the surface. So again, that goes back to what we know from our experience here on Earth. We think that long period of time is necessary for life to maybe get more complex. So when we talk about trying to find life on Mars, or maybe life on Europa, or on other moons of the solar system, like Enceladus that was at the bottom of the graphic that I showed a minute ago, we're not talking about little green men. We're more talking about little microbes. So this is going to be life that's going to be a little bit hard to find in our own solar system. And so when we think about that, we start thinking, how are we going to find it? Let's think about Mars. We've been sending these spacecraft. They have very sophisticated instruments. So what do we look for? We look for the building blocks of life. We look for organic molecules that might tell us that some process is going on. We look for something scientists call disequilibria. We look for things out of balance. Is there something that seems to be consuming something and giving something else off? So those are the things we look for scientifically. But ultimately, I'm a field geologist. I go out and break open rocks and look for fossils. Those are hard to find. So I have a bias that it's eventually going to take humans on the surface of Mars, field geologists, astrobiologists, chemists, actually out there looking for that good evidence of life that we can bring back to Earth for all the scientists to argue about and say, is this life, is it not? How do those cells compare to cells here on Earth? Do these microbes that formed on another planet, do they have RNA or DNA like life has here on Earth? These are the questions that ultimately I think it's going to take our astrobiologists on the surface of Mars to answer. So that's why NASA is so focused on our journey to Mars. And what are we doing to accomplish that? Well, for one thing, as John and Jim Green were talking about, we have a healthy program of studying the surface of Mars right now with spacecraft like MAVEN, with our Curiosity rover. In 2020, we're going to send a new rover to Mars that's going to move us even further forward towards understanding Mars's habitability and performing some initial experiments to get us ready to send humans to Mars. We're working every day up on the International Space Station with our astronauts to understand the long-term effects of spaceflight on human health so we can get astronauts to Mars safely and return them back here to Earth safely. And that's what the one-year increment with Scott Kelly and Mikhail Kornienko is all about. And the twin study that we just started conducting a few weeks ago with the successful launch up to the International Space Station. It's why we're doing commercial crew and commercial cargo. It's why we're developing the Space Launch System, our new rocket that will move humans out beyond low Earth orbit, and the Orion capsule, which we just tested successfully in December. So we have a whole program to move us forward on this journey to Mars, because again, if we come back to the scientific question, are we alone? Getting astronauts to the surface of Mars to help answer that question. Understanding the sun and its behavior and its effects on life here on Earth, but also helping us use that information to understand the potential for life on worlds around other planets. Using our great telescopes, like Hubble, and in the future, the James Webb Space Telescope, to start using the information we're gaining from understanding life here in our own solar system to understand beyond our solar system. Thank you.
Thank you all. Okay, I'm going to do something a little different here. Normally, I'm up here and we're doing a press conference, and the Science Mission Directorate is always doing press conferences because they always are making great news. We're going to obviously go to the media, ask questions here and on the phone line and social media. There's a lot of buzz out there. Send in your questions to #AskNASA. But I see a lot of folks. We have a very diverse audience here. This subject affects every one of you in this room, the folks hearing my voice, watching NASA television, and on our website, and of course, social media. So we're going to transition. If you have a question, just wait for the mic. We're going to start here. We're going to go to the phone lines, and we're going to go to social media. So if we can get this gentleman a mic here and give you a name. And
Hi, Randy Shostak, reporter with EOS at the American Geophysical Union. Thanks very much for doing this briefing. I wanted to ask each of you, what surprises you the most in the recent studies and findings about the search for water and habitable planets, and what are you looking forward to, what most excites you in the coming few months?
Well, I think that, some scientists would have predicted and have predicted plumes on Europa. But I think the serendipity that we are planning a mission to Europa and that Hubble has observed these putative plumes gives us an opportunity for the first time to not only try and understand the structure of Europa as an icy moon, the thickness of the crust, the composition of the surface, the density, the gravity field, all the things that we've done previously in our orbiting missions. But it has the potential to allow us actually to interrogate the plume and see if we see any signs of what might be subsurface life on an ocean on Europa. It's an opportunity that we're exploring. I think that's going to be really fantastic to be able to do that. But that it's not just Europa, that potentially we have Ganymede. And we do see plumes on Enceladus around Saturn that Cassini has been interrogating and has seen very intriguing signs. And that's something you might ask Ellen more about as a Cassini investigator.
So from my perspective, I think our science community is making enormous progress in various ways that I couldn't even conceive of. And that might be because I've scared the heck out of them in the sense that I've said, I'm planning to be the director of planetary science when we discover life in the solar system, so they better get busy. And as I said, it's just such an exciting time for us. Going out to Europa, building the spacecraft we need to do that. Mars, in terms of being able to look at that geological record, go back in 2020 into what we now can recognize are past habitable regions on Mars. Really interrogate another region like Curiosity is. Man, I don't know what we're going to find there, but we're going to save the geological record for potential return back to the Earth. So we're making these huge strides along the way, and I really think and I should bet Paul this, that we'll find life in the solar system before we find it in exoplanets. But we'll find it there too.
What's your record betting, Paul?
Okay. Before I see if we have any other questions in the audience, and then we're going to go to social media. We have some folks I want to recognize in the audience. Dr. Green's talking about getting busy. These folks are getting busy every day. First, the new program director for the James Webb Space Telescope, Dr. Eric Smith. We all know we celebrate 25 years of Hubble. You ain't seen nothing yet after James Webb Space Telescope gets up there. Thank you, Dr. Smith. And behind Dr. Smith is Dr. Mary Votek, the director of astrobiology, and she's getting busy because she's got some conferences coming up where these folks are getting together. And as Jim said, things are moving to answer these questions, and they're moving fast. Any questions from our audience? We have, yes, sir. Please identify yourself.
Thank you very much. My name is Kai Torstulaine. I'm from Rovio Entertainment, makers of Angry Birds, and perhaps more importantly, Angry Birds Space.
Welcome.
I have a question for you regarding today's announcement. So many interesting advances. What would be perhaps the single most exciting thing that you would like me to take back to the entertainment and to the youngsters of the world?
You know, when I go out and talk to student audiences, you know, I always tell them I'm almost jealous of them because to me, they're living in a world in which, you know, maybe I'm a little slightly less optimistic than Jim, that within all of our lifetime, though, we're going to understand that there is life on other bodies in the solar system. We're going to understand the implications of that for evolution of life here on Earth. We're going to find planets around other stars that we can say we see potential signs of habitability in their atmospheres. That's all going to happen in the next 10 to 20 years. How exciting is that? We're on the verge of things that people have wondered about for millennia. Are we alone? And here we are on the verge of finding that out. And I tell the kids, you better study science and math and engineering. You better be practicing your computer skills on Angry Birds because we're on the verge. And we need you guys to study because you're going to have so much work to do studying these planets, these potentially habitable worlds. So you better get to work because we're going to need you to be our scientists of the future.
Good. Any other questions before we go to social media? Yes. The gentleman here. You get him a mic, please.
Mike Helton. Is there any consideration by NASA to take a look at these rocky planets that you are discovering with other instruments like radio telescopes to maybe pick up any kind of radio signals from them, assuming that they might be some advanced system like we have? And we're, after all, sending out radio signals outside of our solar system.
So NASA doesn't operate the radio telescopes that are used, but I know that the operators of those telescopes think very carefully about whether that is a useful investigation to do. The particular rocky planets that Kepler has found are very far away, and so I haven't done the calculations to know if radio signals analogous to the ones that the Earth gives off would be detectable with today's radio telescopes. But that would be the right calculation to do before one decided to undertake such an investigation.
Now, there actually are some observations in our solar system that might help inform what we might do next. And that is, we know that planets that have magnetic fields and they're bathed in the solar wind, that interaction actually produces radio emissions above these aurora that occur. Now that may not tell us that that planet is habitable so much as it tells us about the magnetic field. But we're finding it when we look at Mars, which did have a magnetic field at one time in its past, and now it doesn't, and now its atmosphere has been stripped away. There might be something there that we ought to continue to do research on, but radio telescopes could be used to look for planets that have magnetic fields and generate these radio waves in natural ways.
Okay, let's switch gears and see what's going on social media. My colleague, Felicia Chow, what's the conversation like out there?
Well, Dwayne, there are a bunch of social media questions on NASA's search for life. Daniel Robinson from Twitter asked, do you think life could have evolved out there that would have been hostile to what we understand, such as nitrogen-based life forms?
Who wants to take that?
You know, obviously we're very biased by what we understand of life here on Earth, and pushing the limits to that, what the limits to life are, is something that we have scientists looking at, you know, that question. But certainly the basis that we understand for life, carbon-based life, we know those building blocks are not only all over our solar system, but we know they're all over our galaxy, they're all over the universe. So given that the right building blocks are out there, given that there's water out there, that's what makes us really lean towards looking for life like it is here on Earth. But certainly even in our own solar system, when we look at a place like Titan that doesn't have liquid water, but it has seas of liquid methane and ethane, we've got scientists who suggest maybe you could form some sort of cell membranes even on Titan. So maybe in our own solar system, we'll be able to push the limits of this theory already.
Thank you. Related to that, what role does gravity of a planet play in the chances of it being habitable?
Oh, you got to have it.
I guess the follow-up question to that from Lassie Rooney would be, is presence of water or magnetic field more important for life? And the priority and optimism for Mars, Europa versus Ganymede?
Well, as I mentioned a little bit earlier, the study of the magnetic field and its interaction with the solar wind is such an important element for us to understand how that might have protected the Earth over millennia. And we're doing that by having MAVEN at Mars and looking at how Mars, which no longer has its magnetic field, and how its atmosphere is being stripped away. So I think we're recognizing now how complicated, but yet connected, the kinds of phenomena like gravity, like rocky bodies, like magnetic fields, and like water is playing in developing an environment for life, and then also maintaining it for long periods of time. You know, we're at a time when it's just a snapshot of the evolution of our solar system. And we need to think about times in the past when life could have started and where they could have started. When we look at Mars today, we're actually going back in time in these regions where it did have water. We're going back, and perhaps there's the moment when life actually started on Mars, and maybe we'll find that environment. And then we'll understand a lot about life's origin and put it in the context of how the solar system evolves.
I think the other part of the question Paul answered earlier, which is at the large scale, when a rocky planet gets more than about twice the size of the Earth, and if it's a rocky planet, so it has that density, it starts to accrete more gas when it's forming and ends up like a Neptune, a frozen gas world. And so that probably sets a limit to life on a planet that's much larger than a couple of times Earth.
Thank you. So Dr. Newmark pointed out that the importance of having a magnetic field. Lady Signet asks, is there a way to create a synthetic magnosphere?
I'm not really sure if you need the synthetic for the long term for life. Again, it's important, but as Jim was mentioning, it's the evolution. It's the interaction, of course, with our sun or a local star and that planet over a long period of time is what we're looking for, and how that evolves, not sort of a short-term magnetic field that protects current life. It's really the long-term evolution of life that this becomes important for.
Now that said, we have done studies of creating relatively small magnetic bubbles around spacecraft for future interplanetary and maybe someday future interstellar travelers to have their own protective magnetic field.
So Felicia, before we go to social media, I want to tell you where you are here. I'm being told we have a lot of questions coming in. I tell my TV audience and the folks on social media we're not going to be able to get to many of them, but send those questions in, #AskNASA. We'll get those answered as soon as we can. I also want to tell our panelists that I'm going to like to close with each one of you giving your personal views and maybe a crystal ball or predictions, however you want to do it, but the personal human being, personal views of how close are we, what does this mean with all of these assets what we're finding, how close are we? Are we going to answer the question sooner than we think? So think about that. So let's take one more question from social media, then we're going to wrap it up.
Okay, great. Here's some questions mostly around exoplanets. So what is NASA's current definition of a habitable zone, and what are the requirements for the planet to be habitable? And what are all the conditions required for one that is habitable versus for life as we know it?
So habitable zone is a fuzzy concept, and scientists argue a lot about what the boundaries of the habitable zone are. The general idea is exactly what I said earlier. It's that region of space around a star where one would expect to find liquid water on the surface. But as we can see in our own solar system, both Venus and Mars arguably fall within that definition of a habitable zone, and neither one of them currently have liquid water on their surface. And so it matters what the atmosphere of the planet is, it matters whether it has a magnetic field, and probably lots of other things matter that scientists are arguing about. So you can't write down a formula for it, but you know it when you see it.
Okay, let's. I'm told that we have. We're going to go to the phone lines, and then I'm going to bring it back on stage for the personal views before we wrap up. And again, for social media, we're going to answer your questions. Keep sending them in. Hashtag Ask NASA. Let's go to the phone lines. Mike Wall, I believe. Are you on?
Oh yeah, I'm here. This is Mike Wall from Space.com. Hi. This one is probably for Dr. Stofan. You were mentioning having astrobiologists on the surface of Mars. Could you mention a little bit about what you think is the role for sample return, in the search for actual life on Mars? Where do you see that sort of fitting into this grander pattern?
You know, I think sample return, that's a great question. Sample return, I think, is important for a couple different reasons. For one thing, I personally think that demonstrating that round trip to Mars is something we would want to do potentially when we're thinking about sending humans. Obviously, they've got to get there, they've got to get back. So practicing getting down to the surface of Mars, getting off, rendezvousing in orbit, coming back. Think of it back to a lot of the work that we did prior to sending humans to the surface of the moon. We did missions kind of like that. So you can look at sample return that way. But certainly if you're going from a purely scientific point of view, there's a lot we could learn from samples returned from Mars. You know, a lot of the instrumentations, if you go into a geology department at a typical university here in the United States, the equipment in geology labs are gigantic. And so it's hard for us to shrink those down and have them be as capable on a spacecraft. We send great instruments, but the instrumentation here on Earth is always better. And so the scientific community for a long time, it's been one of their top priorities, is to bring a sample back, and it remains so.
Okay, before we wrap up, I'm going to bring it back and ask Dr. Grunsfeld to start us off, and we go down the row here. Bring it home, personal feelings about why. I mean, this is an incredible subject. Unfiltered.
Well, as you've heard in all of these discussions about our exploration of the solar system and beyond, we're finding, somewhat surprisingly, that our universe, our galaxy, is filled with habitable environments. And it really does beg the question, if there's so many places that life could exist, where is everybody? And that's part of the question of, are we alone? Of course, we've only been a spacefaring world, for a little over 50 years. So I think it's amazing that we've made so much progress in such a short time, that we have a Hubble Space Telescope that can look at the atmosphere of a planet around a nearby star. Because when we imagined the Hubble Space Telescope and built it, we didn't know about any planets outside of our own solar system. This July, we're going to make our first visit to the planet Pluto. We don't know what we're going to find. And the U.S. will have, by July, been to the first to every planet in our solar system and launched the James Webb, and by 2018 we'll have launched the James Webb Space Telescope, which will allow us access to many more planetary atmospheres, including some super-Earths. So I think that in our own solar system, we have a chance of finding that there might have been past life on Mars or evidence of current microbial life sometime in the next generation of explorers to Mars. Whether human explorers, and I share Ellen's view that the fast progress will be made once we have astrobiologists and geologists on the surface of Mars. But the next generation of space telescope after the James Webb Space Telescope that will be able to get high precision spectrum from a planet around a nearby star, that will be able to see the kind of components in the atmosphere that would be solid evidence that there's some sign of life out there. What that is, again, get a group of scientists together, a dozen scientists, you'll get 20 opinions on what that sign of life might be. But I think we're one generation away in our solar system, whether it's on an icy moon or on Mars, and one generation on a planet around a nearby star. There's one other question, though, that if we find life on Mars, microbial life is going to be, does it look like life on Earth, or is it completely different?
Right.
Once we get out beyond Mars, the likelihood that it's similar to Earth because we shared that material gets very, very low.
Right.
And so that's where I think it starts getting exceptionally exciting.
Excellent. Dr. Green.
So I share all of John's views, but I'll tug on one part of something that he said with a little different angle, and that is if indeed the environments that we're discovering are potentially environments where life could arose, where are they? Well, you know, there's a couple ways to look at that. One, well, complex life like us perhaps doesn't last long. That's a big downer. I don't like that view. And when you think about modern humans, where we actually had an opportunity to change our environment, I believe that started about 10 to 15,000 years ago when agriculture got going. Then we actually are in control of our environment, and that's just hardly a blink of the eye in the time of the solar system. So where are they? Maybe they are us. Maybe we are the first species to continue on. Maybe we indeed have that explorer gene that allows us to leave the bounds of Earth and move out into the solar system. And I truly believe that a species that does that has the opportunity to survive. Once we know our environment, once we know the hazards that are around us and other types of stars that explode and near-Earth objects, et cetera, that climate change, all the kind of hazards that we're uncovering now for the long-term survival of this species. We've just got to continue on the explorer route, and I think we're doing a fabulous job. Let's keep it up.
Dr. Newmark.
I'll pick up right there. Discovery. That really is it. I mean, all of us up here started watching man first walk on the moon, and the pace of our discovery is amazing. As John mentioned, we'll be visiting with Pluto the last of the planets that we haven't seen. With Solar Probe Plus, we'll be visiting our nearest star in a few years. We're just continuing to discover what's out there. So in terms of optimism for discovering life, it's definitely an if, not when. And I'm sorry, it's a when, not an if, of course. We're there. The pace of our discovery is continuing to grow. Our understanding of our physical environment around us and understanding the conditions that enable this environment we're just poised at that edge, as Ellen was saying. And so I'm extremely optimistic.
Dr. Hertz.
20 years ago, so I'm an astronomer. 20 years ago, most astronomers believed that planets around other stars must be common because there's nothing special about our sun. But we thought that it was just way too hard to discover them and that we would probably remain unsatisfied in proving whether that was true or not. Because clever people found ways that we could discover and study planets around other stars with the kinds of capabilities we're currently able to do, we now have directly found over 5,000 planets around other stars. We know that they're common, and we are thinking constantly of more and better ways of interrogating the small amounts of light we can get from planets around other stars and learning about those planets, learning about their atmospheres, learning about their evolution, learning about how our solar system might not be a typical solar system, but other solar systems seem to have lots of planets closer to their star than Mercury is to the sun, or have lots of gas giants, or to have lots of planets in size between Earth and Neptune, super-Earths and mini-Neptunes, that have no analogs in our own solar system. It's such an exciting area of astronomy that when I go to astronomy conferences, I notice that huge fractions of all the earlier career astronomers, people whose hair colors are darker than mine, are interested in studying exoplanets, that it's a growth industry in astronomy. It's the most exciting area. It's drawing some of the most creative and innovative minds in science to trying to understand not just what's going on in our own solar system, but what's going on planets around other stars, and trying to answer the question, are we alone and are we typical even in the rest of the galaxy?
Dr. Stofan?
Well, I'm going to go out a little bit on a limb here, and I'm going to say I think we're going to have strong indications of life beyond Earth within a decade, and I think we're going to have definitive evidence within 20 to 30 years. We know where to look, we know how to look. In most cases, we have the technology, and we're on a path to implementing it. And so I think we're definitely on the road. And what to me is even more exciting is that we can bring all of you along with us, because if you go to our NASA website, look for our projects in citizen science, where we have projects from looking at stars to help classify whether they're potentially likely to have planets. It's a program we have called Disk Detective, to looking at the data that was returned from Stardust, or helping us to understand Mars. These are projects that everybody around the country can get involved with. So don't just listen to us, don't just read about it. Come help us discover whether there's life in the solar system and beyond.
Ladies and gentlemen, please give a round of applause to our panelists today. And I want to thank our TV audience on our website for joining us today. I want to say that this is the official kickoff for NASA's Solar System and Beyond campaign. And you can find out more, because there's going to be a lot more coming, at #NASABeyond. And of course, you can always get updates and information on all of the incredible missions and the Science Mission Directorate and NASA as a whole on www.nasa.gov. And finally, ladies and gentlemen, the next time you go outside and look up at the night sky and see the stars, remember your nation's space program, NASA, has assets and more coming, looking to answer the questions discussed today. NASA is determined, NASA is committed, and we're out there. Thank you.